The y-axis is, I think, mapped directly, so the y-axis you're giving it is just the angle. But then the x-axis is relative, so then you're just like kind of moving the camera side to side, but you aren't telling it like what position to be at. So that was, I think, the best I could get without a bunch of hacking on the gimbal. My favorite thought was this shower epiphany, which is like, I don't want to go there. Let's just actually tap directly into the gimbal. I've mentioned this before, but the gimbal has kind of a distributed architecture where there are microcontrollers on each of the joints. The top joint, which is where the sensor for that angle is actually located, that one isn't moving around. So if we added some wires in there to grab the signal from that encoder, then I think we'd have the signal we needed. We could send it the joystick motion that would be needed to move it left and right, but we would know where it actually is pointed. But as we were talking about it early on the last stream, it seemed like maybe it was worth at least exploring the software solution to this a little bit more, since it seems really likely there's just a serial protocol where I can tell the gimbal exactly what I want it to do. It's just probably a little obscure. We have two more data signals, and those are multi-purpose. Those are used both for pitch and yaw, pulse width modulation from the RC receiver, and they're just bridged right over to the serial port, which is used to set settings and update firmware. The manual's kind of straightforward, not super helpful. Yeah, so you can tell a little bit about what they're doing here. Like the CRC16 is, I think, what we were seeing in the non-encrypted portion of the header. The attitude correction, I'm not entirely sure what this is. I think it might just be like the center position. And I mean, you'd think that maybe you could use this just to aim it to different things. I don't know if it does that directly, but I'm thinking if we can get an idea of what this protocol looks like, maybe there's just a straightforward way of using that same protocol to tell it to do other things. So this thing that looks like a micro USB port, it's not a micro USB port, it's actually a serial port with 3.3 volt. I think maybe it was important to open this and then boot up the gimbal. That was the key. Oh, it's gonna suck if I need this to have power control over the gimbal just to get it back into serial mode. So that third byte right after the header is alternating between 0 and 1, which seem to be the two different packets in this sequence. Those might be different commands. There might be different microcontrollers we're addressing this to. This does look like a polynomial CRC instead of a checksum, based on how it's changing. I really think that first byte after the nominal header that we've been saying, so basically the third byte in the packet, I think the third byte is this MCU ID. But I don't know if we know which functions go to which MCUs yet. So I just followed exactly these steps on macOS using Homebrew, installed these things, the dependencies, then ran the script. So we got the demo device, and we've got that salient logic. Okay, so it does need the firmware. Logic. Yay. So we have two FPGA bit streams. We have the FX2 firmware. Are those the USB strings? This is the FPGA bit stream in BinViz. macOS share sigrok firmware. Oh yay, this is where it wants it to live. Config, that's what I want. So sample rate is a thing. Protocol decoders, this is where it's gonna get fun. Yeah, okay, I think this is how you do out-of-tree development. FY Gimbal, I think, is a good name for this. Annotation, I guess, is the human-readable stuff. Python is for other Python modules, and then binary would go out to a file. Now we've got our hi message. Okay, so this was two packets, and within each of these we have a header, a CRC, and some body. And so RX here is from the gimbal to the PC. So this is the gimbal powering on, announcing presumably its version. Then it spams out these messages that are like, hello, I'm here, please connect to me, or something like that. Someone in chat was saying that this byte might be the length of the rest of the payload. That does look like it could be. So maybe this is a microcontroller number, this is a command type, and this is a command length, and this is the actual data. Let's see if that works. I assume they would need a different encoding for the firmware packets, though, because those are probably going to be more than 256 bytes. This is what the PC software listens for, and then it immediately responds with this to prevent the gimbal from normally powering it up. I think there were a couple of people who mentioned this in chat, but the CRC is a standard CRC16. Then this, I think, is going to be the firmware itself. I think it's got an 8-byte header and then the rest of it's encrypted. The command header, that's the actual firmware data. That is exactly a kilobyte. And this I would expect to be the second kilobyte of the firmware. Oh yeah, that's right, 404. That would totally be the length for this. This one definitely doesn't have a 2-byte length field. And then we'll have another section for A55A packets. So it could be this is the header, and this is the microcontroller ID or something, and this is the command ID, and this is the length. So it is the standard X modem CRC. FF6B, that's what we're getting. So I think this is probably an okay encoder for now. Let's work on the decoder. We know how big the packet is. We don't know if it's valid or not, but no matter what happens, we want to dequeue it at this point. So this is sticking individual bytes in. If any packet comes out, it processes it. So that was the gimbal starting. There's the gimbal shutting off. So you can see with the gimbal shutting off, it has targets 210, command 3, so it's like it's shutting each microcontroller off. So this is the roll. It's very subtle, but when I do this, I am actually moving the camera. So you can see here, those second and third bytes are the actual roll value, but the first byte seems to be the axis. And I want to see if there's a yaw axis at 2. So this was, I think, me setting the different follow speeds. So maybe this is just two 16-bit numbers. Don't know what this one would mean right away. So it received a bunch of those little version indicators, but then as soon as we received this thing, which I guess indicates the gimbal is starting up and there's an opportunity to halt it, we respond with the same command going out to target 0 with maybe like a yes, I do want to halt it. This gimbal has 3 separate control systems basically, but they communicate over a serial bus, and there's some questions as to how the messages are processed, like what jobs are done by each of the 3 microcontrollers. To sum this up, I think that spying on the traffic between, at the very least, the first microcontroller and the second one, which is easy to get to without taking that much of the gimbal apart, I think doing that at the very least would give us some really good information that we could use to try to find useful commands in the protocol that we're using. I figured we would be doing this to get access to the magnetic encoder signals, but now we're doing this for completely different reasons. Didn't actually turn out to be simpler, but maybe just more satisfying in the end. I don't need that either. Alright, let's turn on the gimbal and see what happens. So power supply at 12 volts. Ooh, that's better. What do we got here? That looks like serial. Yeah, that's right at 2 megabaud. So let's try that. That looks familiar. A55A, OO, OD. Wow. Here's the initialization sequence where it's kind of sending out kind of hello messages or something, and it's kind of colliding with the incoming pulses coming from the Raspberry Pi. You can see those messages are also going out on the internal bus. So this is the one we were just looking at that seemed to have 3 16-bit numbers. I think we found the command that the first microcontroller converts the kind of RC servo PPM signals into. So it's a little unclear how these would map to the 2 analog channels we actually have. But it looks like we have 3 16-bit numbers and then maybe a mode setting or something like that as the last byte. So that was the boot up sequence. Here's the Windows software halting the boot sequence. Well, that was actually on 1. A bunch of interesting comms right after that. And then it looks like these are still maybe sensor readings, but we don't have any control coming through. And then if I change settings, you can see it sending that on to maybe the next micro. Jesus! What just happened? This is also not what I wanted. I wonder if this is the same space that we've been seeing in 8. Like if we send command 6s with a bunch of different keys here, will we get a bunch of different values? Is that a way we can dump its settings? Let's try that. My hunch that I'm trying to follow is that maybe this command 6 is returning something from a local configuration space, and like in RAM, and that this is just an index into a table, and that this is a 16-bit number from that table. And my extra hunch is that maybe that's related to the table that we're setting with command 8. But yeah, it looks like we've got a space of 16-bit numbers. This is probably a table entry, some other byte that might be reserved, and then the actual 16-bit number. There's probably a whole bunch of juicy stuff we can set. This might also explain why the gimbal has been drifting lately, like I might have accidentally clobbered one of these values. I think it'd be really nice to just have a program where I can go through this command space and edit all the values. That might even be enough. Like, I suspect there's enough in there that you could probably find a way to aim the gimbal just by editing these. I think maybe I've corrupted some of the settings in there. I can imagine them implementing this a bunch of different ways. This might just be a blob of SRAM that they use for some settings and some runtime values, and then they just save it to flash anyway. I can imagine them having different formats for in-memory, like RAM and flash. I can imagine that this isn't actually in RAM at all, but this is just like a command layout, and they've got a switch statement that generates the values as needed. Let's do the off sequence first, and then carefully the on sequence. It is wobbling in like a figure 8. We know some things about the protocol, but I also somehow managed to accidentally save some settings which caused the gimbal to be unusable. Look at that! We have SWD. Ooh, is that like a readout protect maybe? So it's not actually stepping, but I have a program counter address and I have registers. Ooh, device is read protected, gotcha. Can read from RAM. Got some numbers. Anyone like numbers? Oh, that's pretty. Something awesome happened, and Mark WHI in chat donated this spare gimbal. So the plan here is to open this up, make sure it works, and then try to carefully use the code that I've got so far to slurp out the parameters and save them, and then try loading those parameters onto this other gimbal to see if we can get it working. I do want to be careful not to repeat the same mistake. So one concern I have is that I don't know exactly how the problem happened. There are a couple of candidates, some kind of communication bug or a bug in my script. I ended up sending just like a long string of zeros or something else that was just kind of malformed. And it seemed to be related to a buggy program that I ran. This was a really oversized get command and issued several of those. And right after that, the gimbal just started bouncing against the end stops, and I pulled the power as soon as I could. So my hunch is that maybe I hit a bug in their code, maybe even a buffer overflow. So this outer array is organized from 0 to 128 in the same order that things are stored in memory on each microcontroller, what it looks like. Then this tuple is microcontrollers 0, 1, and 2. So each microcontroller is effectively one of X, Y, and Z in a lot of these values. Seems like a happy gimbal. So no input, but it's already just stabilizing and following the heading. All right, I think we just did it. Let's power it off again and take a look at what we got. I mean, I think we should probably just try splatting these all on and then saving them while the gimbal control loop is off. I think that worked. I'm just going to power cycle the gimbal and hold it and see if it starts acting normally or if it starts thrashing itself. Huh. It was slowly thrashing itself, which is different. Okay, so that's the initial values, And then it just keeps scanning, and anything that changes ever gets set in bold. And so you can see the stuff that's at all dynamic. So what we're looking for is something that is not bold, that has a value in the first position, like the left number, that we think we could change to maybe get a better yaw centering. Yeah, let's change just axis 0 in 6.4 and just see if that has any effect. Wow, we did change the center location. It just didn't really change for the better. So it seems like this axis is now totally wrong, which is axis 1. But maybe we're in the right location. So what did we just change that between? Okay, now it's back to the position that's kind of way over there. Let's try 800. I want to try 800 and see where that takes us. Whoa, different problem. It's still kind of confused. It feels like there's a point in the middle where it like rolls over and doesn't quite know where it is. It's acting like the magnet's on there backwards or something, but I didn't take the magnet apart. And this has kind of been a combination of trying to find parameters that are stable enough we can just get it running so that I can use that as a basis for tweaking it further. And some of this has been actually trying to figure out what the parameters are. Yeah, I mean, this definitely looks like a control loop parameter is just not at all set correctly. But this seems to be maybe a workable starting point for making a little parameter tuning UI for ourselves. That's kind of the flow so far, is I have this program which is slow, but it scans the entire parameter space, and I'm using this to kind of categorize which ones are interesting to look at in real time. And this just operates on strings sent over WebSockets. It receives lines of text, each line is a command, and the lines are based on tokens. I'm mostly adding things based on looking for specific elements with a specific class in the document. Is I can just edit this HTML to kind of give myself a little dashboard, including some, some notes about what's what. But you should already be able to see, like, if I move this, you can see this responding. These are joint angles. A lot of these aren't labeled yet. As far as I can tell, 2C is the most processed output from the magnetic encoders. These seem to be angles between 0 and 4095. You can see the rollover point right there was 4095 to 0. And stuff like this, like, I think these are likely gains or offsets that are not calibrated per device, but were just kind of typed in somewhere. Well, so 4D is that thing that we thought was the stored center location. Yeah, 4D and 6.4. We might not need the graph, but I'm just going to keep this for the moment so we can watch how it responds. Okay, so this is 4D is the one that we had been assuming was the center location. Setting it over a particular value caused the yaw to go sharply in one direction, even though that was not the yaw axis I was changing. Now it's going unstable and drawing like 90 or 0.9 amps. I'm going to turn off the motors. Okay, so here's what we've got. The negative 400 is just something I made up that seemed to be better than what was there before. I don't know what that actually is signifying at the moment. Then the other two, I think, are copied from the dump from the good gimbal. This seems like it's all right. Well, I mean, clearly I don't understand what I just did, but it's nice to know that it seems possible to improve the situation. Oh, it's still a little wobbly near the center. What about this one? Whoa. Oh, geez. Yeah, I need much finer control over these parameters. This feels like an offset, like there's a point around which it just wants to pull really hard to one side or the other. Like that just feels like the axis has been gained down a lot, like it's really limp at responding to the yaw. It doesn't feel like just a gain parameter, it feels like something more complicated. Oh, interesting, yeah. This is now locking into the wrong positions. I'm at like 2090, and it's like it's off by an entire motor phase or something. And now around 2100, it's not a sharp cutoff though, it just goes from holding kind of the wrong position. It's still drawing a good bit of current. It's like 800 milliamps total right now. Yeah, this maybe isn't a gain. Maybe this is like some kind of phase offset for the motors. Because it feels like maybe I'm having the effect of decreasing the gain, but maybe what I'm doing is decreasing the motor efficiency. See, I bet this parameter is motor related. I bet this is a calibration for the motor, the offset between the motor phases and the magnetic encoder or something like that. Yeah, maybe the thing that's calibrated at factory isn't the gain at all. Maybe the thing that's calibrated is mechanical parameters of the sensors. Anyway, maybe this is a good time to take a look at the firmware. If you look at the .bin, it looks pretty encrypted. The flash readout protection was set up, so we couldn't just read out the decrypted firmware. But I made a RAM dump. And then based on this RAM dump, MakoMK, who's in chat right now, thanks so much, they were looking at the RAM dump for potential AES encryption keys and found a candidate that turned out to be right on. I think the method was just brute force decrypt using all of the, all the different values that we found in RAM, just try everything and find something that's low entropy. There's like a length up here and a pointer, so this is the beginning of some data structure. And then this is actually the internal state of AES, so this is the key schedule after the key's been expanded, and this is the actual key itself. And we already knew from some earlier poking around in this, kind of the overall structure of these firmware files. The first 8 bytes of this is actually a header. This is actually probably a checksum. This also shows up in the Windows software as a CRC16 of some sort. Then this seems to be the size of a firmware image for each of the 3 microcontrollers on the 3 axes. And then everything else in here is organized in 1024 byte blocks. The empty areas of this thing all seem to be the same block repeated. And so that seemed to be an artifact of the encryption mode they're using. It looks like AES CBC mode. Okay, so that worked. So just for some more context, this is the version of Unpack where we're using a key that we found in RAM. We're using an AES mode that we guessed based on the repeated blocks that we were seeing. And we're using an initialization vector that's all zeros for now. So it's already looking a lot more plain texty than before. You've got some structure here, but it doesn't quite look right. We're pretty sure that we have these blocks that are either 0 or FF. Each of the first 16 bytes of each of those 124 or 1024 byte blocks, this is going to be the initialization vector XORed with the plain text, which in this case, I think the plain text is 0. So in that case, this is just the initialization vector. Now we're actually seeing some signs that this might be correct. So if this is the beginning of an image, this is looking like an interrupt vector table. We have a stack address, which is in RAM. We have something that might be an entry point in Flash. We have some other Flash addresses. So that's our firmware image. And so because we have 3 microcontrollers, there's a separate firmware for each micro. This is a nice trick for just checking out the entropy. We can see that the middle micro is a little bit smaller, and there's some code that's specific to the first one and the last one. Yeah, this would probably look more interesting if we graphed these as 16-bit numbers, but I'm assuming this is some kind of math lookup table. ROM section. So I'm going to start this at the beginning of Flash right now, even though I'm pretty sure that's incorrect. But D2FF minus some other number should maybe give us some code. 2 Flash blocks. Like, if this is right, it means the bootloader's like 16K. Would they have a 16K bootloader? Is that realistic? That'll go 16K after the beginning of the Flash. This is looking right so far. These are all interrupt handlers that just go to infinite loop stubs. More functions. A lot of unused entry points. So a lot of these are probably boring. one of them is probably serial and is probably going to buffer stuff in a queue in RAM, and then something maybe in the main loop will handle the commands. I wonder if this is the incoming serial port and the one down here is the outgoing serial port. Critical section over here, I'm guessing it's storing stuff in a FIFO. Is this the address we prepared earlier that points to the data register, maybe? So the serial 1 FIFO is used in the serial 1 init, in the ISR, and then maybe this is part of what we're looking for down here. Serial 1 FIFO. Looks like we're reading bytes out of the FIFO here. Ah, okay, so this is actually like a polling function and it sends the results right here. Ooh, is this going to be their serial state machine? Oh man, this is totally the protocol state machine. There's the 5A. So 18A is the offset to the actual payload buffer. Packet CRC update. So maybe this is actually just checking, is this for me or is this for the other microcontrollers? So this is actually probably related to read broadcasting a packet that's designed for someone else. So now this is receiving a local packet, 14 cases. So let's just go right to something that that we might care about. Let's do like getting commands, because a get will tell us how it replies. It'll also tell us where the commands are, or the parameters are stored. So the get command is command 6. Anyways, we're building a reply header. This is a get response. So it looks like we already have the result. Yep, this must be the parameter base. Alright, I guess those are just stored in RAM. 24C should be where the parameters start. And it looks like they're just one-to-one mapped, which means I would expect to see the version and stuff here in the RAM dump. That might be it. That's the version at the end. So, now that we know where the params are in RAM, we could actually take anything we don't know about and try to match it up to this area. This switch statement maps directly to these commands now, which is pretty nice. So, command 8. Oh, command 8 is really little. Why do we have the ability to set with 16 bits of reach? That seems like a bad idea, unless they're truncating it, which I don't think they are. This just goes straight to memory. So this command is very dangerous. This just writes to RAM starting at the location there, but you could easily just like splat whatever you wanted later on in RAM. So any experiment I did where I set that second byte of this packet to a non-zero value would have just written stuff elsewhere in RAM, and that could have easily caused the crash that I ended up having. This is what the PC or whatever is on the serial link sends in order to break the normal initialization sequence. Case 12, that is undocumented currently. That's command C. Oh, that's doing something else with parameter RAM. Command C. It's just copying from this value to that value. Maybe this is for capturing a center. Oh, and it looks like it can store it in one of two different places. My guess is that they have two different reference positions they need to store. Maybe one of them is related to the center that it's supposed to hold at, and the other one is related to like a mechanical center for the motors or something like that. I think the gains are all just set ahead of time. I don't think the gains are calibrated. I think the calibration just consists of two reference points. So I think what they do in the factory is I think one of them is the center and one of them is something else that's relevant to how the motors are lined up. And then based on those two reference points, it calculates all the other factors it would need. So I think that's why we were finding that, if I was adjusting one of the reference points, it would seem like in a particular range it was affecting the gain, and then it would like hit some point where it would cross over and then the gain would be negative. And so I think what we were actually seeing was there was some other gain-like factor that was being derived by subtracting those two reference points. So this is command OC, which I've been calling unknown. I'm going to call it calibrate. So if we give it this calibrate command with a parameter of 0, that's locking in the center position. But if the parameter was 1, now we're storing this, so it's the same structure. We're copying the magnetic angle to some other thing. In this case, this is another old friend. This is the parameter that I had been assuming was something related to the motor alignment. And I wasn't sure what the units were, but this makes it pretty obvious that it's also another angle. I just don't know exactly what that angle points to. So I think that's the next thing to do, is to make a little tool for checking the calibration on an existing gimbal, like an existing calibrated gimbal, and then run that on our working gimbal and see what that actually points to. And I think we just want to print out the current angle, the calibration slots, and the differences between them. I think that's working. So I'm going to try to hit the stored calibration point 0 first, which I expect to be the center. That seems very centery. So the diff from cal 0 is near 0 when I point the camera straight forward. Okay, let's try hitting the other stored parameter now. I'm going to have to take out the camera because that doesn't quite reach. These seem like very arbitrary positions. So I'm wondering if this has something to do with the way the motors are aligned. What we're looking for is something that would be relevant as a reference angle. So, you know, like, of course there's a bunch of stuff that's arbitrary about the angle sensors, sure, but what is this referencing? You know, maybe I should just get this back into the reference 1 position again and maybe mark it or something. I'm just frustrated because I think the next step here is going to be taking this gimbal apart and looking for alignment markers. First I'm just going to put down 3 reference marks, which are just at arbitrary locations. And then for each axis I'm going to put the corresponding mark right where it lines up to calibration point 1. I'm just adjusting this until I hit 0, and then placing the marker. I'm also thinking about, like, how would they do this at the factory? I wonder if this is done at an earlier stage of assembly with just raw boards, or if they have a jig that they put the entire thing into that just lines it up just right. Yeah, so there's the mechanism. You can see, so this is the motor. The wires are feeding through the center, and that thing the wires are actually feeding through the center of is a magnet. The magnet's just glued in a kind of arbitrary orientation as far as I can tell. And then right under it, that 8-pin chip on the circuit board is the encoder. That's weird. That's close to lined up, but actually is not that close. You can see the motor connector is right there, and the bar is right there. I wonder how much of this is arbitrary. I wonder how much of this is just they built a test harness at the factory that happened to line things up a particular way, and then they copied it. Don't know what else to do other than manually copy these angles over to the other device. Okay, that's close to the reference, I think. So let's just give this the actual defaults now. Set defaults. Then I have it close to the position 1 already, so let's do this next. Cool, we got a response. And let's try the other position now. Okay, another confirmation. But let's try hitting the motors. That seems pretty subtle, doesn't it? I mean, the center's a little off, but power consumption is really low. I think we unsaddened our gimbal. Ooh, look at it follow. Oh, that's beautiful. I think we unsadded the gimbal. So there's still some question marks as far as controlling it properly over the serial protocol. The firmware that's responsible for the PWM inputs that's normally disabled when I have that in serial mode, I think that is calculating like basically a velocity at some point that the loop integrates. And so I think I probably just need to figure out where that is and like set it to 0 or set it to the value that I want. So like just to bring this back up to a slightly higher level discussion, what I'm trying to do right now is to try to find, so I know how to calibrate the gimbal at this point, roughly. The next step is how do I control it? And so I've seen this command 1, which I can send, and I can get the first micro to reproduce to the next one. But I'm trying to figure out how, like basically how the input path between joystick and internal state works, and which pieces of that I need to provide on my own when I boot the micro up in serial connection mode. So one open question still is, are we going to need to patch the firmware? The biggest reason I think to maybe patch the firmware is to get this thing to always come up in the mode where it's listening for serial commands. So github/scanlime/fy gimbal. Everything we've been doing is going here, with the exception, of course, of actual firmware dumps, because like that stuff is lawyer bait. These are the outputs of some of the control loops, like the follow loop. But when those follow loops are off, then this will directly command the gimbal velocity. So that should be the state we're in right now. So if I command the yaw control rate right now, this should directly move the gimbal. And it's pretty smooth. This is just controlling the angular velocity that it's trying to hit on that axis. And if I turn on that follow loop, which if I set this axis to 1, whoa. So you can see there was an impulse on that control rate, and then it settled down to around 0. So now it's driving. And it's actually settled out to mostly straight on. I think we're going to see it follow now. Check that. And you can see the waveform of the actual follow motion. And you can also see it's got like a linear, I think it's like a piecewise function where depending on how far away it is, it has a couple of different speeds that it goes to. So one thing that you can do is, since all of this is just like a shared pool of RAM that all the control loops are reading and writing that you can also read and write, you can see like if you're sending something but it's also being overridden by something else, then you can see like little impulses get through. So like if I move this, you can see it kind of jerk back and forth a little. And you get a similar effect if you try to set these control rates for pitch. Not quite at the same time scale, but if I give it a speed, then you can sometimes see a little vertical nod get through, but mostly it's returning back to a set point. So I took a little closer look at that, and it seems like there are 2 different versions of this control loop that are selected between, depending on whether or not you have this follow mode on or off. Both are actually setting this control rate, they just do it in different ways. But then this one should be the follow mode for pitch, which selects between those 2 different loops. So the effect of that is to hold it at a level horizon. And it does so pretty much immediately, like it isn't kind of trying to approach it with a very slow motion, it just goes straight to that. So this is just trying to be subtle about it, but it can also go fast. If you go really fast, you can slam it into the end stops, which I would avoid doing, but hello, other camera. If only we could aim up. So that's really the next thing. Yaw is doing what I want, but pitch is not working. Pitch is pretty different here, and I was trying to command it by sending it kind of fake joystick packets, the same as the third microcontroller would normally get from the first microcontroller. So I've been looking at all 3 of these firmwares to some extent in IDA. I've kind of gone the deepest into the first one, since it's related to the communication directly with the PC. Another big ol' switch statement. So now you've got a bunch of new commands. So these are all the commands that the last microcontroller knows about. So the one we're interested in is the joystick command here. Where's that? Here it is. It's like right after the jump table. So Command 1 joystick. Right. This is just ignoring joystick commands when the PC is attached. So I guess we're patching this. Okay, well, the first step to patching this is having our own firmware packer and update tool. So these are all AA55 commands, like all of it. So that supports the theory that the two different packet types are actually two completely different code bases. So that micro is saying, hello, I'm a bootloader. And then the PC is saying, oh, you're a bootloader. Wait, stop booting. We have stuff for you to do. So that's the bootloader command 1. And then it just starts sending blocks. There's no like, please prepare a buffer for this or something. It's just, hello, have a block. Maybe what this command does is it puts that micro into a pass-through mode, and everything after the 8 is then communication with the next one in the chain. Enough procrastinating. Let's brick this thing. It's still alive. Great. That's a good sign. And this should be in follow mode again, because it's just running normally. Maybe the first patch to make is something that keeps it in serial mode, because that's seeming super useful now. This is the code we're replacing. Normally it's calculating a pitch movement speed, which gets written to this control rate vector. And as you can see, there are a bunch of ways we can end up there. There's no way around it though, and I would like to write that myself, since this code is not being super cooperative, and calculating that value on my own seems like a really nice clean interface boundary between the two sides of the gimbal, basically. The really low level side and then the high level heading tracking. So my jump destination will be 800B416. I can just splat over this basic block, basically. Yeah, because, I mean, if I could just have a shell script that applies to patches using Radari 2, that might be exactly what I want at this point. So I have a little script here which just unpacks the firmware, runs a Radari script on each of the binaries, then repacks it. And currently the patchers for the first two should be empty. Nothing yet. And for the pitch axis micro, we just have that one patch to jump over the whole follow loop, which should be straightforward, but of course, plenty of opportunities for stuff to go wrong. So while this is compiling, maybe let's look at MCU 0 and see how we can keep it in serial mode and prevent it from disabling the serial port. I think maybe we want to even go as far as having it know that the PC is attached, not just have it not disable the serial port. This is the command that we'd already seen the kind of Windows software that comes with this gimbal issue in order to keep it in serial mode so that it can send commands and read parameters and all that fun stuff. So this has to happen at a particular time. It has to be sent after we're done with the bootloader and we're in kind of the normal gimbal firmware, but before it's actually finished booting up. So we should actually see a place in main where it's sending out one of these command Bs to the PC. And this is actually the response where, okay, the PC is attached. So all this is doing is setting a flag. It's setting this PC attached flag. I think what we want to do is just go back to the code that sends that initial command and figure out how we can put together a minimal change that'll cause that to just end up setting this flag and continuing on without having to wait. This is the loop where we are waiting for the PC to attach. This serial poll is, so we've already kind of stumbled on what we're looking for. So send packet to next MCU. This is, I think, sending on a successful connection to the next micro. So I think we do actually want to get here, unless we just make this change to every micro, but it seems easiest to only make this change to MCU 0. These are the solicitations asking the host to connect. So we don't necessarily need this code, but if we changed this, then it would like break compatibility with some of the tools that are waiting for this command. So it would be nice to keep this intact, but perhaps only send one of these and act as if we got a response right away. And one way that we could do that is just immediately after sending this, we could just set that main flag PC attached to something. Maybe down here we repurpose some of this, since I don't think we actually care about reading a response at this point. Maybe we repurpose this to be a set to write this flag, to set this flag back to 1. And then next time we go through this loop, we would send the packet on to the next microcontroller. Like, we can overwrite these 3 instructions if we want to with our own stuff, since we won't need them. You know, I'm feeling lucky. Let's make a patch for MCU 0 also. So we already have this R4 base address, which is super conveniently pointing right at our PC attached flag. So if we convert this back to an offset, we can see that it happens to be at base 0. Well, let's put a no up there. I think that'll be the right length, but we definitely need to take a look at that. So yeah, these are both double width instructions in thumb 2. So we can overwrite this with 1 instruction, then we overwrote this with 2 instructions. Now that gets us to here, which we could leave that intact. This will actually operate very, very similarly to the original code. It's just instead of checking the serial port and polling, we just end up setting the same flag. But it ends up setting the same thing at the same time. The only difference is that we don't end up processing other serial commands if those happen to come in. Let's test this. Patcher, patcher, patcher. Alright, so it is operating normally now. Following and everything. Look at that, happy gimbal. So, power off. FYI flash, firmware / assembled.bin. Flashing! Okay, so it's written, if I reboot it now, what I expect to happen is that the gimbal should stay limp, it shouldn't power on the motors, and then if I run one of these other programs after powering it on, it should still connect, whereas before it wouldn't have, because it would be in PWM mode. So, power cycle. Well, so far so good. It's dead, which is what I was hoping at this point. Let's see if we can talk to it, though. Paramdiv. Oh, look at that. We are so communicating with this gimbal now. This is good. This means I don't need a load switch for turning on the power only after I have the serial endpoint running. All right. So if the change we just made had the effect we wanted, what I'll expect is that this follow mode for the yaw or the pitch axis should no longer have any effect. And if I adjust the control rate for that axis, then this should actually work now. And the X control rate is hooked up to the joystick right now. So if I move the joystick, you'll see the X rate changing. But nothing should be driving the pitch rate right now. It works! Oh, come back. No. Okay, it's a little tough to respect the end stops manually, but yeah, that's working. And see, I can start this up and it doesn't move at all, like it keeps its previous heading. I think we should look at the video output from this. I bet it's going to look good. The large dead zone is a little bit too big, maybe. It means it's hard to move it diagonally. It's much easier to move it in a straight line. Having it be like a vector dead zone instead of a linear dead zone might make that a little easier. Oh, this is great. Let's just make that camera full screen. Can steer this around. Hello. Here's me. If I like swing back and forth. But yeah, this is feeling pretty interactive. This is all based on reverse engineered commands and patched firmwares. That seems to be doing what I want. The follow loop is totally disabled on both of those axes. But I can still manually point it. Oh, there's some shimmy. That's going to need some calibration. Anyway, I think this is about the wrap-up point for this stream. I feel like we've got a pretty, made some pretty good progress on this. We have a binary patch to the firmware that kind of sets the mode the way we want it to be. Like, imagine having this thing track a particular object even as you move it around. Like, we have the input for that now. That's super exciting to me. Oh, maybe the gyro angle is what I want. Because that's the camera versus the horizon. Oh yeah, that's what I want. That updates right away, and it's pretty smooth. Oh, that's nice. And 0 should actually be the horizon in this coordinate system. Yeah. That's great. So now I can just have my own servo loop, move this with the speed that I want, or try to hit a particular position, or whatever. It's up to me now, which is great. So I've got speeds out and positions in, which is great. Well, folks, I think that's about it for this. If you want to play along at home, as always, we've got the files, at least the files that I created in GitHub, and the firmwares you can download. Go to scanlime/FY Gimbal. The controller that we were just running is this script right here. And the binary patch now is in firmware. You can find some scripts for packing and unpacking the firmware blobs, and these little Radare scripts for the actual binary patches that we just did. Thanks for tuning in, as always. Happy we got to cover so much ground and use a variety of tools here. It was nice using Radare in addition to the usual IDA here. Well, and that brings us to the end of this epic recap edit. If you made it this far, thanks so much for sticking with this reverse engineering journey that brought us through from having a pretty decent working gimbal that was going to be a little annoying to control, to completely breaking it, and then finally bringing it back and then giving ourselves a much nicer serial control interface. So if you enjoyed that, check out some of my other videos in the scanlime series. You might enjoy some of the other kind of rapid, in-depth edits like this. And if you might enjoy seeing some of this work in real time, then subscribe or follow the Scanlime Live Twitter account, and you might catch up with some of our real-time broadcasts. Well, thanks to everyone watching this. Thanks to everyone who participated in the real-time streams. And a special thanks to all my patrons who support these streams with monthly donations. If you think you might be interested in supporting these broadcasts and these edits in the future, then if you head over to patreon.com/scanlime, then you'll see some more info about what I'm doing and how you can help out.